Okay, we are continuing with our small signal model before we start amplifier. Typically, as we have so far solved equations, the equivalent circuit of a MOS transistor is shown here. This is your gate, this is your drain, this is for common source, this is your source which may or may not be grounded, in some cases it may be, and then there is a bulk, and we believe that all capacitances are right now not relevant in the low frequency range. Essentially it means 1 upon omega c is such that it open circuits everywhere. Okay, so assuming that, you can see there is a input voltage of VGS which is equal to input voltage of Vn, and since gate has no connection resistively to the source, this is open and therefore Vn is equal to VGS. At the output side and the drain side, you have the current source which is Gm times VGS or Gm times Vin, plus, and there is another current source which is due to the VSB substrate bias, which will give me a GMB VSB term shunted by R0 as the output resistance. Now if this is the low frequency model, and in many cases since we are interested in the MOSFETs or MOS circuits bandwidth, which is the frequency at which gain is at least reasonably constant, for those frequencies we will require capacitances, and this is an equivalent circuit which is called high frequency small signal models. This is most important, all this analysis always has been done for small signals, and the issue we shall raise little later, if there is not enough small signal word satisfied, what do we do? Okay. That is one of the major issues right now in most new devices and circuits. You can see from here, source has small resistance Rs dash, which is the source region resistance, N plus region resistance Rs dash. Similarly there is a drain region resistance which is Re dash. The rest part is similar. This, then there is a capacitance across the CGS, gate to source capacitance, which we declared as VGS, and there is a capacitance between drain and gate which we call CGD. Then at the output side there is a GM VGS as the one current source, GMB VBSB as the another current, same as this, plus, and they are 0, so they are same. Now what is difference is, there is a capacitance between gate and bulk, sometime it gets screened, sometime may not get screened, but we should show it. In case it is screened, we just remove that. And there is a resistance which is associated for substrate, okay, that is called RSB. Then there is a capacitance between source and bulk, CSB. Then there is a capacitance between drain and bulk, CDB, and there is a resistance of the drain side which is RDB. Now these are essentially equivalent of a diode, you know, R into parallel C is what the RC combination. So these are those resistances in capacitance. R normally are very high, so open circuited, but as a logic we must put them and then say okay they are large, small, and may remove them out, okay. But this is total small signal high frequency equivalent model of a MOS transistor, and in case you want to solve this, the easiest way is to figure out the values of each of them, and there are number of loops or number of nodes, whichever way you want to solve Kirchhoff law, you will be able to solve V0 versus Vn relation. That is what we are looking for at the end, gain V0 by Vn. Since I have enough nodes or enough loops, I can solve as many unknowns as many nodes or as many meshes, and therefore we can always solve this circuit. We will give a small example to show how do we solve that. In all analysis, please take from me that this may be a very good this, at the end of the day we will not solve actually all the circuit by hand, but to start something on CAD we need some hand calculations. So in that hand calculations all model can be simplified because you are only trying to get the first guess, okay. In that case all these detailed values may not be required in many hand calculations, though there can be some error in hand calculation. I will list them out what happens if you do not take care enough in case of designs. However, this is the model which we will be using for a MOS transistor, and this is shown common source, but it does not matter, you can tilt any angle to make it common drain or common gate, whichever way the circuit remains, or the equivalent circuit remains same. Let us say it is n channel, all these device, unless said otherwise, devices are n channels. If there is a CMOS part there, we will explain that CMOS again. Okay. There is a resistance associated with this region and there is a resistance associated with this region. After all, there is a semiconductor regions and they may have heavily doped, so the resistance may be very small, less than 5 ohms or 3 ohms sometimes, depends on the area. Now that is where the problem started. Why we started looking into it? If you see rho L by A as the R, you may actually reduce rho because of doping, higher dopings, but this area also is going down because you are scaling. So if you scale down, this area may not be as what it was earlier, it may be 100 times, 1000 times lower. So essentially R may not be as small compared to what we thought in the long channel devices. So please take it that why this new models have added these terms, because they may be dominant terms, not very dominant, but they may actually change the pole positions or zero positions, and therefore one must take care in solving any Kirchhoff law on any circuit. Is that clear? In normal case we neglect them, we say it is few ohms, the others are kilo ohms, so forget it if they are in series. But if they are in shunting, then they will be the one who will matter most of the time. So one has to take care of all this in writing. As circuit requires comes, we will remove the terms which are not relevant in evaluations. Is that okay? N plus. This is like a 3-dimensional device, okay, a 3-dimensional resistor. Okay. So this is a bar of semiconductor which will have some resistance rho L by A. Okay. Okay, so this is what we keep saying you, that this is needed because in case you are using accuracy, then you may need them also. Okay, so another method of solving the same amplifiers which I earlier did, this is my method which I always say that you can look at the solving any equations or solving any circuit by very different small signal analysis, not really very different but interesting way. So I just always want to show you how do I can solve other ways. Let us say this is a common source amplifier which is biased by a constant current biasing, which is constant current biasing is IDS is constant, fixed current source. Right now I also assume it is a good ideal current source. What does that mean? The output resistance of that current source is infinite. Okay. In real life, if I replace this by a p channel device as a current source, its R0 will actually come into picture. Is that correct? Right now it is assumed constant current source ideal. In reality they may have to be modified for the real R0 comes there. So this analysis is this is a technique and there is nothing great about these solutions which otherwise you will get. We know this current IDS flowing in this transistor is a function of Vg and function of Vd, which is a standard MOS transistor theory. I can use my partial differential kind of partial differentials of this to equate some terms. I say okay, change in IDS must be equal to delta IDS by Vg into delta Vg step. Similarly for the Vd, delta IDS by delta Vd into capital delta, which is a step function. We know by definition change in drain current with gate voltage is essentially Gm. Change in drain current with Vd drain voltage is essentially G0. Okay. So we rewrite delta IDS is Gm delta Vg plus G0 delta Vg. If I convert into differential forms, it is delta DIDS is Gm dVg plus G0 dVd. In our case, change in Vg is essentially the input signal, AC signal, so Vn is dVg, V0 is dVd, which is the output AC signal, which is nothing but change in the drain voltage is because of the small AC signal which is applied at the input. Is that okay? This is, as I say, many people believe that this is better way of explaining the two port parameters which you must have learned or you must be learning now somewhere, S parameter, AV parameter, H parameter. How do we get parameters from any transfer functions? This is how we get it, okay. So that is the technique I am showing you. How do I get two port network solutions? This is how one can try any two ports or any n ports, in fact, longer difficulties in solving. So now I have equation delta IDS is del Gm del Vn plus G0 dVd, okay. So here is that expression which it will appear. May I put it now? So I get delta IDS is Gm Vn plus G0 V0. As amplifier is biased in constant current source, there is no change in current, okay. So delta IDS is 0, which is equal to Gm Vn plus G0 V0. If I take a ratio of V0 by Vn, it is minus Gm by G0. G0 is the output conductance, which is 1 upon R0, so it is minus GMR. That is the expression we derived, okay. This is called intrinsic gain of a MOS amplifier. Why it is intrinsic? No load resistance was used. Instead of load we have constant current source with infinite output resistance for that. Is that clear? So this is Gm times R0, okay. Now if we take the first order model using an RD now instead of constant current source, and let us say there is a series resistance with the source, and let us say some capacitance CGS is taken care, and right now assume that CGD is open circuiting at a frequency of my interest. Then I say Vn is Rg, equivalent, so there is a CGS which is holding the VGS voltage, then it is Gm times VGS R0 shunted by Rd. So this is, and in all these cases VSB is taken 0, that is source and bulk are grounded. Unless specified, do not use those terms. If I specify something or indirectly specifying it, look for that value and substitute in GMB VSB terms and solve for it, okay. What is that you have to do is just add many times 0.6, 1.1 plus 0.6 GM is good enough as the GMB equivalence of that. So you need not solve many times, just add, instead of 1 put 1.6 and you can get rid of much of the solving. This is for hand calculations, so this much assumptions may not be very absurd, but in real life you may have to calculate actual values given doping, given everything, and then figure out what is the GMB values you get. Okay, so if this is my equivalent circuit, why I am doing it, I want to give some numbers which is very interesting in designs, and that is why I am trying to look for them. Is it okay? This is equivalent circuit, there is nothing great, all that I put 2 terms here and additional term RD here. So this is still low frequency, that CGD is open circuiting, 1 upon omega CGD is still infinite enough to neglect, open it. So the transfer function from output to input, which is the gain function AVS, which then can be written as Gm R0 parallel Rd. I should have put a minus sign here because a phase opposite, okay. Now we can use some derived values for Gm, CGS, R0 which we already derived in our device theory. Earlier we said Gm is 2 IDS by VOV, which is VGS minus VT, the excess voltage. So those who have taken a course of my analog like Survey is there and many others, there is a difference in approach when I come to design a course. The basic I cannot change, I mean analog amplifier will give me gains, but how do I derive and how do I actually get design for it is what I am now showing. So it is nothing extraordinarily different from what we learned in second year, but even then it is worth looking at it. The CGS value we calculated other day, it is 2/3 W by L Cox in saturation. If you wish you can use 1/2 Cox term as well, 2/3 can be made 1, but if you want to keep, and I do keep sometimes, so I am keeping it, but as I say if someone puts it, there is nothing very absurd will happen. R0 is 1 upon lambda IDS, which is the current, then AVS and AV0 is defined as, sorry it is minus everywhere, is GM parallel R0 RD. You can see from here, sorry I will just put it and come back. The current in this parallel resistance of R0 RD is what GM VGS current is flowing through. So minus GM VGS into R0 parallel RD is my V0. So that is what exactly is GM R0 RD is my DC gain, and if you say RD is much smaller than R0, it is minus GM RD. If R0 is much smaller than RD, it is GMRO. Which case this will occur? The first one is normal resistive loads. The second is the case when the biasing is constant current source. Okay, in that case R0 will be RD will be much larger compared to this, and in that case probably this term can be that is why I say intrinsic. Okay, so intrinsic case. So once we do this, so what is the trick I am trying to show you? I am trying to derive some expressions for GM-IDS and GM by CGS. So these are the two expressions I am going to use in my design. So I want to get those expressions from what I am writing. I normally use a term which I will show you later, RO parallel RD is small ROD, which is RO parallel RD, and then you can replace it by either RO or RD, depends on the values. Okay. Or you don't, you solve it and automatically one of the term may go if it is much smaller or much higher. Okay. Is it okay? So having done this, if ROD is R0 as I said, in that case AV0 is minus GMRO, then I can write R0 by AV0 is 1 upon GM. From this expression 1 upon GM magnitude wise. Okay. Then I say GM by IDS I know is 2 by VOV. I know GM by CGS is 3 by 2 I had derived last time, mu V by L square. Then these two terms I will call them as figure of merit for analog designers. I repeat, which are the two terms I am going to design for? GM by IDS and GM by CGS. Please take it, this GM by CGS is essentially FT, and we will see what that term is. Okay, that is why it is called figure of merit. GM IDS is a figure of merit because it decides what? It decides some way the power, it decides the bandwidth, and therefore the gain as well. So that is the figure of merit. Okay, so what is GM by IDS and what is GM by CGS will decide every aspect of an amplifier. So these two terms I call it as figure of merit. Okay. So what is the major decision for any analog designer is to choose proper VOV. You can see expression everywhere, you are only seeing VOV. So if you can choose proper VOV so that the power dissipation, the gain and the bandwidth specs are met. Is that correct? So what is the designer spec? VOV. Is that clear? VGS minus VT. How much excess voltage you want to keep for the bias requirements is all that matters in decision of making power dissipations, gain as well as the bandwidth. Is that correct? Somehow though I am keep telling you all this, and then I say I do not like this VOV term very much, and I will revert back to saying I will not use this, but initially I may say okay, VOV is a great term which allows me to design every spec which I am really looking for. So choice of VOV, typically what do you expect the value of VOV should be in a smaller technologies now? Any idea? Let us say I am working on 1 volt supply, what should be typical VGS minus VT will be? 0.2 volts. So typically it will be around 200 millivolts is kind of VOV values you will have to choose. So one technique is fix VOV, do something, or fix something else and let vary VOV. Okay, so we are trying to design based on these features. Okay, okay, so is that clear? So VOV in my opinion is one of the major factor which defines the circuit performance. What are the 3 parameters I am looking for in amplifier? The gain, the power dissipation and the bandwidth. Okay. One term which I have not said, maybe I will have separate chapter to that, separate talk a lot many on that, which is the noise part. We are assuming as if everything is nice for us. In reality the killing part will come from the noise part and also temperature part, which we assume as if everything is fine. All models are fitting into all our requirements, which may not be really true. Okay. So the whole why spice or why everything is because all such variations analytically solving for all of them simultaneously becomes very clumsy, not that impossible, but very clumsy. So it is much easier to go on a CAD tool to solve that. Okay, so if we see this expression which I wrote here, okay, AV01 plus SRGCG, same expression which I had. Now HS is 1 of GMR0RD1 plus this. So if I now substitute gain function as AV0 1 plus SRGCGS, RGCGS has a some kind of a time constant, means it is a pole sitting right there. Okay. Now please remember, if we have done our second year course well, which we I hope so all of you have done. So if I plot frequency versus gain, and I figure out for certain frequency, till certain frequency gain is constant, and then of course it goes down and goes down like this. Of course this is a 3 dB point where the gain falls by 0.7, but as a Bode's plot we can actually connect two slopes, and this frequency from where the gain starts falling is our bandwidth, okay, up to which gain is constant. Now few things I must know. I want to increase this A, that means I am really looking for something like this in real life. I want larger gain, larger bandwidth, and also in turn power should not go up. That is what I am asking myself, and then I will say, "Arey baba, itna nahi, kuch do mujhe." Then I will say what I can actually work with, so that the third parameter may help me to get what I want. So 2 I can get, maybe third I will have to give up. So within a given range, if I can fit that, then I say I have designed an amplifier. Is that okay? So my worries are bandwidth, gain. What is this term essentially? If I plot it in dB, then this is 0 dB, unity gain. So this is the point G gain into bandwidth, is that correct? And this point actually we may like you can do like this, okay. You have many ways of moving this point, okay. So we will see how can you play games, that means how many capacitors are around and where they sit and where these poles positions can be changed to suit your requirements, okay. Sometimes you additionally put capacitance, sometimes you see to it the capacitance are not really strong there, whichever way we can adjust, we will see to it what can be done. Is that okay? So design means given a spec, how do you play with? So we already said that the gain bandwidth, this RGCGS is related to bandwidth now, because that is the only pole available to you. So we therefore say, in the case of circuit shown by me, no CGD and no output capacitance, the dominant pole or the only pole available to you is 1 upon RGCS, and that is the one which will decide the bandwidth. If we write now CGS as 2/3 WL into Cox, we can write, also we know GM is mu Cox W by L into VOV, we have derived this expression earlier. From here I find out Cox from here and substitute in CGS. What do? From this GM expression I get Cox value and then I substitute in CGS value. Is that point what clear? I use the second equation, GM is Cox mu VOV, evaluate a Cox something like this, GM L by W VOV to the power minus 1 upon mu, and then I play little game. I say okay, if you see carefully, GM R0 or ROD whichever you say is the gain, GM RO is the gain. So gain by RO is GM, so I replace GM by AV0 by RO parallel RD, or you can keep one of them also, into length R L by W, which is the aspect ratio 1 upon VOV into 1 upon mu. If I see very carefully now, this W0 if I substitute back here. Now CGS I have calculated this long expression, I substituted in my bandwidth terms 3 by 2 ROD by RG 1 upon AV0 mu upon L square into VOV. This is the expression I get for my bandwidth. Why I did all these calculations? I am looking for gain into bandwidth, and I am also looking which term will actually vary for what I am looking for. There are 3 terms there, I will show you, I will write down, I will show you this. If you finish this, I will show you what I meant. I repeat, my worries are power, gain, bandwidth. So I am trying to see expressions in a different form, so that I will see which term, like say power, which of the terms in power expressions which will actually enhance the power, or which will reduce, then reduce the power. But if I reduce this, I will come back to the other expression, see if that term varies here, what will happen to the second expression which I use, W for example. So I keep writing expression for each which are of relevant for me, and I keep playing games to see which term is dominating for me and when I can control. Is that design issue clear, Surabhi? Is that now you understood why second year to fourth year there is a issue, okay, or rather fifth year sometimes. Okay. So the issues are, that is the design part. So please remember why we have a separate course on analog design, VLSI design, because there we only solve something, okay, and we say it is fine, it comes like this. Now we are worried, given something, how do I match it, okay. So this inverse process needs much thinking, than, because there are many possibilities which may do that, okay. Which one is better, but if you choose one, then the other may hurt, okay. So where do we get hurt, which terms are important is design, okay. So is that omega 0 term is clear? So I write now same expression, if I put it here you can see now W0 is 3 by 2 ROD by RG into 1 upon AV. Normally these are specifications for the amplifiers, gains are functions, RG is external resistance of the source, which is generally 50 ohm to 600 ohms, depends on the source you use. ROD is normally RD if you are putting a resistor there, that is something which you have fixed. If you are putting the channel length, somewhere you are fixing RO, okay. So this we say is essentially specs related. First few terms 3 by 2 ROD by RG into 1 upon AV0 is the specs related. The second term there is mu by L square. This is not in my hand, it is a technology, people will say okay, this is the best mobility I can give, and this is the length of the technology node I have used, 0.18 micron, 0.13 micron, 90 nanometer, whichever technology L and mu is decided them, we have no control whatsoever on them, okay. So this is whatever technology gives, that is the spec for, I mean you can't change, okay. Let us look at the power, dissipation is, IDS is the current, power supply is VDD, so the DC power dissipation is VDD times IDS. If I substitute that IDS expression from this I can rewrite, please check it, AV0 related to GM, please remember what is gain, GM times ROD, is that correct? GM can be written in terms of, what is that, IDS by 2 IDS by VOV, manipulate expression, that is what I keep telling you, I just manipulate few things. So I get half VDD by ROD, AV0 and VOV. Now we observe, if I want to reduce power dissipation, what should I do? This is all fixed,